theorem describes how will then heat flow from a source reservoir to a sink reservoir. From here, we can see that heat is actually flowing from the hot reservoir, which is the source, to the cold reservoir, which is the sink, by the means of a heat engine, which is doing work against the surrounding. This theorem describes the relationship between heat energy and temperature exchanges for a reservoir. Well, let's first take in mind this diagram, that is some hot energy and cold energy. Let's take them in mind. Previously, we saw that heat energy was directly proportional to the temperature for a given reservoir. So if we take both previous cases into consideration, let's say Q2 is the heat content of the sink and Q1 is the heat content of the source, the hot reservoir. The heat content of the sink would therefore be directly proportional to the temperature of the sink, and the heat content of the source will always be directly proportional to the temperature of the source. From this expression and from the mathematical expression which we had, which was Q on T is equals to K, we can establish some expressions as heat energy of the source divided by heat energy of the sink will be equals to temperature of the source divided by temperature of the sink. So if you do some algebra exchanges here, you will get to see that heat energy of the source divided by temperature of the source will be equals to heat energy of the sink divided by temperature of the sink. Send this one on the left hand side and you get heat energy of the source divided by temperature of the source minus heat energy of the sink divided by temperature of the sink is equals to 0. This describes like a change, that is, if the source energy was like state 1 and the sink energy was like state 2. Here we are kind of getting a cyclic change, which we have here, which we have in this expression, as the cyclic integral of change in heat all over temperature is equals to 0. This is actually important to know. From the previous expression, as cyclic changes were equals to 0, we are able to establish after some work through that the integral for the first change of change in heat divided by temperature at that level will be equals to the integral change of change in heat for the sink divided by temperature of the sink. This shows that the integral described whatever the path taken will always be the same. This means that the integral describes a change in property, because if dq on dt, if the integral of dq on dt is always the same, whether we are talking about the source or the sink, therefore we are not looking at a path function now, but at a point function. If it is a point function, then we are describing a property, and that property, let's call it ds. Spoiler alert, ds is entropy, but for now let's call it ds. Let's call that property ds for now. Clausius inequality, how does it goes about exactly then? If we say that the cyclic integral of dq on t is actually a property, that is, whenever you see dq on t, this is actually a cyclic integral of, maybe just to write it back, but dq t here is the cyclic integral. So the cyclic integral of dq on t is ds. Carnot's efficiency, that is the perfect system, tells us that 1 minus the temperature of the low energy reservoir divided by the temperature of the high energy reservoir, this Carnot, will always be greater than the efficiency of an irreversible cycle. Note it, heat movement from hot to cold is actually irreversible spontaneously. That is, you will not take, it's impossible for you to it's impossible for you to take the energy that the air has absorbed and send it back into the hot coffee without an external agent acting on it. That's why it's an irreversible process. So it cannot efficiency describe the best possible efficiency. This best possible efficiency will always be greater than the efficiency of our irreversible process. Therefore, using this same expression, we have 1 minus temperature of low divided by temperature of high source will always be greater than 1 minus temperature of low divided by temperature of high for an irreversible process. So we conclude that temperature of low divided by temperature of high for a Carnot process will be greater than temperature of low divided by temperature of high for an irreversible process. But we know that Q1 divided by Q2 is equals to T1 divided by T2 from our derivation previously. So we get this little expression that is Q1 divided by Q2 is less than or equals to T1 divided by T2. The previous equation implies that Q1, the temperature of the source divided by Q1, the energy of the source divided by the temperature of the source, is less than or equals to Q2 divided by T2. But we know that Q2 divided by T2 is actually ds. So Q1 divided by T1 is less than or equals to ds. But we also know that the cyclic integral of dq on t is equals to 0. It therefore means that dq on t is less than or equals to ds. This inequality is actually Clausius inequality, and it permits us to establish a relationship between heat energy and ds. I said that ds was entropy actually. So it means that there's a relationship between heat energy and the entropy of a system. But now, how is it related? From this equation, actually, we can conclude that ds will always be greater than or equals to 0, since we said that dq on t is equals to 0. So ds will always be greater than or equals to 0. What does this mean exactly? What does the change in entropy being greater than or equals to 0 mean? From the equation derived, two conclusions are actually possible to be established about the property ds. Let's imagine that ds, that is change in entropy, is equal to 0. Then the energy of the system and its surrounding is at maximum. What does it mean if ds is equal to 0? If ds is equal to 0, we say that the energy of the system and the surrounding is at the maximum. I will take it at the span of the universe, for example. It means that the energy content of our universe, the small universe of the system and its surrounding, is at the maximum possible. But now when ds is greater than 0, then the energy of the system is actually decreasing, because the entropy is that is, as entropy increases, the energy content of the system is actually decreasing. This inequality of entropy can be related to the fact that the universe is finite. That is, one day, whenever maybe you might be still alive, maybe you might not be alive, maybe you might be in a million years, no one knows. But actually, the universe will end up dying, because when the universe, let's go to maybe the Big Bang, for example. When the Big Bang occurred and there was maximum energy in the universe, the entropy change was 0. But now, as we progress further and further into the age of the universe, the energy content of the universe is decreasing. Therefore, the entropy is quite increasing. So there will come a point where the entropy will be so large such that the energy of the universe is 0, calling the death of the universe. So entropy permits us to actually relate. Entropy permits us to actually relate energy and maybe the life of a system, for example. Many would define entropy as a measure for the rate of disorderness of a system, which is quite an accurate definition, because the higher the entropy, the more disordered the system is. Let's still look at the state of the universe, for example. A high entropy universe, that is a universe that is tending to die, is one in which the expansion has been so much such that the stars, the planets are so much scattered, so much disordered, but the energy is quite decreasing. That's when the entropy will be the highest. So thank you everyone for listening to my video on entropy, and I hope that it helps you understand better the topic, and thank you very much.